Hello, I'm audible. Hello. Oh, okay. We will start in few minutes. Let's start the job. No, today is the second session. So we should start now. Oh. So first I will introduce the course or what is the course. So this course is numerical methods, finite difference approach. Here we are using finite difference techniques in order to solve the partial and ordinary differential equations. And the instructor for this course is Dr. Amiya Kumar Nayak, and he is from IIT Roorkee. And I am the your TA for this course. My name is Yudhvir Singh Yadav, and I am from IIT Madras. I am a research scholar at IIT Madras. So in last lecture, we have discussed about different numerical techniques in order to solve the ordinary differential equation. And as per this week lectures, we will discuss the numerical methods to solve the partial differential equations. So first, we will discuss what you have done in the previous week, and along with it, we will do some assignment problems. So the first concept is the one-sided approximations. In this, we basically are solving a function in which we only need one side points, like on either on the right hand side points or on the left hand side points. So let a function a plus bx plus cx square Now it can be solved straight away. Like if we want to solve at n equals to 1, that is at x equals to 0, then we will have f1 equals to a. This scheme can be written as fn plus 1 equals to a plus bxn plus cxn square. Here we are try to find the iteration at n equals to 1. So from here we will get f1 equals to a. At n equals to 2, we have x equals to delta x, where delta x is the step size. And for n equals to 3, we will have twice of delta x. We will just keep on adding the step sizes. So this is like a straight away method, and simply you can solve in using the same fashion. We can easily find the values of the required function. So we will now proceed to the partial differential equations that should be our main focus. So here we will try to construct numerical difference scheme for the parabolic equation. Or we can say we are solving the heat equation. So we consider a heat equation del U by del T equals to del 2U by del x square with given boundary and initial conditions. So the initial condition is, and the boundary condition is on both the ends of the heat rod. So here we can see that the order with respect to T is 1, so there will be only one condition. And order of the spatial direction is 2, so there should be two boundary conditions in order to for this equation to be well posed. So in so to solve these kind of partial differential equations, we have different type of numerical schemes. So the first one of them is a schematic scheme. So in schematic scheme, as we have discussed in the last session, that we have forward difference, backward difference, and the central difference. So we just substitute them in these in this partial differential equation. So for del U by del T, we will substitute our forward difference scheme, that is, and for the double derivative, we will use the central difference scheme for second order derivative. So after simplifying this, So here we will get the schematic scheme. If we substitute delta t by delta x square, say lambda, then a schematic scheme is plus lambda times ui minus 1j plus 1 minus 2 lambda uij. So this scheme is called the schematic scheme. So this is an explicit scheme. As you can see on the left hand side, we are trying to find the solution at the j plus 1th level, whereas we only required only the jth level solutions in order to find that. So it is an explicit scheme. Next, we will try to find the truncation error for this scheme. The what is the order of the error? So that is the main part of any numerical scheme. So we denote the truncation error by tau ij. Basically, the truncation error is nothing but the difference between the exact solution and the uh, finite difference and the solution of the finite difference scheme. Let's say small u is our exact solution minus the capital U, that is our finite, that is a solution of our finite difference scheme. So our PD is for heat equation is del U by del T minus del 2U by del x square. We will take the left hand side on the right hand side and we will expand. First, we will write its scheme. What is the schematic scheme? So schematic scheme is or it can also be written as in terms of x and t. And next we will use the Taylor series expansion of all these terms. And we try to cancel out the terms. So the truncation error will be the remaining terms that we are left with. So for the first term, in first term we have in tj plus 1, so in the time direction. So we will expand its Taylor series in with respect to t. So it will be uxi tj plus k, let k be the step size in the time direction with the first derivative del u by del t plus k square by t square del 2u by del t square It can be like expanded after these terms also. Then for the next term, we will expand with respect to x. Let h be the step size in the x direction. So Taylor series expansion will be del u by del x plus h square by 2 factorial del 2u by del x square and so on. For the third term, we will have the expansion as u minus h del u by del x plus h square by 2 factorial del 2u by del x square and so on. And last term will stay as it is. Now we will try to cancel out the terms in this expansion. So if you see, then after cancelling the terms, we will be left with k del u by del t del 2u by del t square plus like in further terms in the expansion with respect to t del 2u by del x square. So we'll be left with these terms only. Here one can note that we don't use the higher order terms. We will take the least term, that is the del cube by del 3 cube del 2 in the third term, that is del 3 u by del t cube. We don't use that term, or they will cancel out after we expand it to the some other term, up to some other terms. So here if we simplify this, a lambda we have like k by delta x square or k by h square. So we can write it as k by h square multiplied by the inside terms, that is s square del 2u by del x square and so on. If you note that from the first term and the fourth term, we will have k common and del u by del t minus del 2u by del x square. And from here we have k square by 2 del 2u by del t square minus k h square by 12 del 4u by del x square and so on. So our first, the heat equation is del u by del t minus del 2u by del x square. So this term will become 0. Here we are left with the other terms. So from this term, if we take, we can write it as k square by 2 del 2u by del t square and so on. So for the order, here we can see for the order of this scheme will be of order k plus h square. Because if we take common in this, in the last equation, that k, if it is common from all the terms, we can k common out. So, and we will get one h square term with respect to del u by del x. So then the order for this scheme is k plus h square, which is a linear with time and or second order accuracy with respect to x. So the second scheme, or we will first take one question on schemated scheme. So the question says, using schemated scheme, this one. Here, the truncation error is nothing but the difference between here u is the exact solution of the differential equation, and capital U is the exact solution of finite difference scheme or finite difference equation. Is it clear? Oh, here earlier equation is that del u by del t equals to del 2u by del x square. So we just simply take all the right hand side on the RHS and substitute with their finite difference scheme and expand with using the Taylor series expansion. Hello. You can speak if you want, like, hello. We have first constructed the schemated scheme. Here we have taken the second order central difference scheme to substitute del 2u by del x square. So we simply first constructed the scheme that is given by this star. And here also you can take all the right hand side terms on the left hand side and then substitute the Taylor series expansion. We have done the same thing. Is it fine? Yes, we are substituting the del to u by del x square by the second order central difference scheme. So this term is nothing but the skimmed scheme we have substituted here. Okay. So in this question, we will have the initial condition as sine pi x, where x is from 0 to 1. And the boundary conditions are also the step size is given as h equals to 1 by 4. So here we will try to find some iterations with respect by using the skimmed scheme. And lambda is given as 1 by 6. So first, here we like what the skimmed scheme is. So this is the skimmed scheme. And in question, we have given with h and lambda, but we do not have the step size in the time direction. So first we will find that. So since we have h equals to 1 by 4 and lambda equals to 1 by 6, so as we know, lambda is nothing but k by h square. So from here we will get the value of k, and it will be 1 by 6 and 1 by 16, that is 1 by 96. And also we have x is from 0 to 1. So we will have the step sizes as 0, 1 by 4, 1 by 2, 3 by 4, and 1. And for time, we will be having 1 by 96 and 2 by 96 and so on. And from boundary conditions, we have that at both the boundaries at x equals to 0 and x equals to 1, we will have u equals to 0. So this can also be written as u 0 comma j, that for all values of j, it is 0. And u4, that is this fourth node. Since it is 0, 1, 2, 3, 4. So u4 comma j is also 0. And from initial condition, we have ux is sine pi x. So from this, we can find at every point that x equals to, at every node, that u0, we know that we will try to find u10, u20, and u30. So u10 will be nothing but sine pi, and at 1 we have u equals to 1 by 4, so it will be sine pi by 4. this will be sine pi by 2, and this will be sine 3 pi by 4. Sine pi by 4 is nothing but 1 by root 2. Sine pi by 2 is 1, and sine 3 pi by 4 is again 1 by root 2. So we have these much points or these much data from the question. Now we'll solve the schemated scheme. So this was our scheme. So for first time iteration, we will put j equals to 0. So step 1 is at j equals to 0. So we will have u I comma 1, 1 by 6, since lambda is 1 by 6, u I plus 1 comma 0 plus 2 by 3 u I comma 0 plus 1 by 6 u I minus 1 comma 0. Here we will have, say this equation is 2. Now we can change, for at this time step, we can change the values of I. So first say I equals to 0, then we will have, or we will start from I equals to 1. So it is u 1 comma 1, 1 by 6, u 2 comma 0, 2 by 3, u 1 comma 0 plus 1 by 6, and u 0 comma 0. So from this data, we already have the values of for this u. So it will be 1 by 6 times 1 plus 2 by 3, 1 by root 2 plus 1 by 6, 0. So this is nothing but it is 1 by 6 plus 2 by 3 root 2, or if you calculate it in decimal form, it will come out to be 0.63807. So this is the first point, that is U11. In similar fashion, if we put I equals to 2, then we will have U21. So it will be 1 by 6, and substituting all these values, and in this at this step, we will also require, we need U30 plus 2 by 3, U2 comma 0 plus 1 by 6, U1 comma 0. So again, we already have these values. So it comes out to be, you can calculate it, or I will write the final answer. So it will be 0.9023689. Next, we will take I equals to 3. So U31 is 1 by 6, U4 comma 0 plus 2 by 3, U3 comma 0 plus 1 by 6, U2 comma 0. So it comes out to be U31 is 0.63807. And similar way we can do it for j equals to 1. For j equals to 1, you will put, it will be uij I2 1 by 6 ui plus 1 2 plus ui minus 1 comma 2 plus 2 by 3 ui1. So in similar fashion, you can solve for j equals to 1 also. Next scheme we will see the Lasnan scheme. Yes, yes, okay, yes, okay, okay. Okay. Yes. You will be allowed to carry a scientific calculator. So these problems won't be that tough. You can either leave the solution at the fractional only, at the fractional part. So you don't need to solve the like decimal place, but if you have time, you can solve it. But if it's a pen or paper exam, then I don't think you will use MATLAB or some computer language. Yes, 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 yes. You have to do manually. So either they won't ask you to solve like many iterations. Either they will ask for one iteration or two iterations. So if you solve it by yourself, then it won't take that much time. It will take around 10 or 10 minutes only. Yes, yes. As per my knowledge, like the questions will not be that tough or not computative. Either they will be straight away. Yes, yes, yes. You have to do manual. Most more than you just can only use a scientific calculator, not anything then else. Softwares won't be allowed. Yes. So the next scheme is the Lasner scheme. Here again we are solving the heat equation, that is del to u by del T and del to u by del x square. Again we have the same boundary conditions and the initial condition. So I will directly construct this scheme. So here what we are doing is we use a backward difference scheme for the time derivative and the central difference for the spatial derivative. So it will be, so this is the scheme. Here I have taken del t equals to k and delta x square as h. So after simplifying this, we will arrive at the final scheme, that is, so this is a Lasnan scheme. Now here you can see that, sorry, this is equals to u I comma j. So here as you can see that we are using j plus 1th level solutions in order to find the jth level solution. So this kind of schemes are said to be an implicit scheme. Now again to find the truncation error, we just simply substitute their Taylor series expansions and cancel out the terms. So I will write one or two steps only. So say tau ij is the truncation error. And again that del u by del t minus del 2 u by del x square is taking out on the left hand side. And the next term is minus lambda u xi plus 1 tj plus 1 minus the term on the right hand side, that is u xi minus tj. Now, when you expand it, it's using the Taylor series expansion, or we say after further simplifications, you will get the following terms, or you will be left with the following terms. That is k square by 2 del 2u by del t square minus 2 del 2u by del x del t minus h square by 12 k del 4u by del x4 and so on. So if you take k common from these terms, then the order of this method, order of this less than method will be k by 2. So we will take the first two terms and neglect the rest of the terms. So here the order comes out to be k plus h square. So it will be linear with time and second order with the space. The next scheme is Crank-Nicolson scheme. Here we have the heat equation del U by del T equals to del E. This one is of more importance than the previous ones. So here the initial condition is, say, some function this, and boundary condition is so the second order and the first order in time, it means that while we like iterate in the time direction, so about what rate we are converging towards the solution. Like if it is of linear order, then it will take more time to reach the, like we have one exact solution, but here we are trying to find a numerical solution through a numerical approach. So here we will see that if we have a linear order accuracy with time, then it will take more time to reach the exact solution, or in order to match that exact solution. But whereas if we have of order 2, like if we have order of k square, then it will be much faster and much accurate than the linear order. So higher the order, higher the accuracy and the rate of convergence of the solution will be. I will this one. So here we also again taken k common, then there we will be left with one coefficient that will be k and one will be h square. So here also the order of the scheme is k plus h square, that is linear with time and second order with the space. Is it fine? No, we will take k common from all the terms. Like we will take the term common which is present in all the terms. So here you can see that k square is in the first term, second term, and so on. And in every term, k is common. So we'll neglect that term. Or you can, like if we have truncation error, say tau ij, we have some truncation error, then the order will be 1 by k times of that. So we will either you take k common or divide the whole last term by k, then that will be the order of your scheme. Is it fine? Hello? Okay, you can recheck it whether the order equation. Okay. So we are on the Crank-Nicholson scheme. So in Crank-Nicholson scheme, while constructing this scheme, we will do it in two steps. So say first one, we will apply forward difference scheme in the time and second order central with space. So it will be u ij plus 1 minus u ij by delta t, or we simply take it as k. And here we will use second order central difference scheme. It is ui plus 1 comma j minus u2 ij plus ui minus 1 j divided by h square. So let us say 1. In the next step, we will apply backward difference scheme for the time derivative and central difference scheme for the space derivative. So it will be uij minus uij minus 1 by k, and this side will be same. Now what will we do is we will replace the term j with j plus 1 in the second equation. Then we will get ui plus 1 j plus 1, 2 ui j plus 1 plus ui minus 1 j plus 1. So say this is equation number 3. Now we will take an average of the equation 1 and equation 3. That is, we will add up equation 1 and equation 3. So adding 1 and 3, we will get twice on the left hand side, twice of uij plus 1 minus uij divided by k, and adding the terms on the right hand side. So from first we have ui plus 1j minus 2 uij plus ui minus 1j by h square, and the second term is ui plus 1, it is ui plus 1 j plus 1 minus 2 ui j plus 1 plus ui minus 1 j plus 1 divided by h square. So now again we will simplify this equation. We have h square common from both the terms on the RHS. So the final scheme will have uij plus 1. This will be k by h square. We will take it as lambda. So it will be lambda ui plus 1j minus 2 lambda uij plus lambda times ui minus 1j plus lambda times ui plus 1 j plus 1 minus 2 lambda times ui j plus 1 and lambda times ui minus 1 j plus 1. Now, taking the j plus 1th level terms on the left hand side, we will get lambda times minus lambda ui plus 1 j plus 1 plus 2 plus 2 lambda. If we take it common from both the sides, that is ui j plus 1 and minus lambda ui minus 1 j plus 1. Whereas on the right hand side, we will be left with lambda times ui, only the jth level terms. So it will be 2 minus 2 lambda uij plus lambda times ui minus 1 j. So this is our Crank-Nicolson scheme. Now we will take one problem in which we will try to find the order of this, uh, the truncation order of the Crank-Nicolson scheme. So this is our scheme. So here we will first write it as we have done in earlier two cases. Suppose tau ij is minus lambda ux I minus 1 tj plus 1 plus 2 1 plus lambda uxi tij plus tj plus 1 minus lambda uxi plus 1 comma tj plus 1, and taking the right hand side also on the left hand side, and it will be lambda u xi minus 1 tj minus 2 1 minus lambda uxi tj minus lambda times uxi plus 1 tj. So this will be our this is the form of we have in the truncation array in terms of I, xi, and tj. So here we will use Taylor series expansion again. So the Taylor series expansion using this, and we expand the following terms. So tau ij will be equals to minus lambda uxi tj. Here we are expanding it with respect to two terms, like on in x direction also and t direction also. So the expansion will be, so since it is xi minus 1, so it will be u minus h del u by del x plus and plus j plus 1 in the time direction. So we will take j plus of k. So it will be k del u by del t, then h square by 2 del 2u by del x square plus k square by 2 factorial del 2u by del t square, and one term is minus 2hk del 2u by del x del t, and so on. Plus, for the next term, we will have 2 plus 2 lambda. So expanding the second term, we will only have the time direction iteration. So we will with this we will expand it with respect to t only. So it will be u x tj plus k del u by del t plus k square del 2 u by del t square, and so on. And the third term again we have with respect to I and j. So we will have minus of lambda u xi tj, and here we can see we have both in plus one, I plus one and j plus one. So all the terms will remain positive. So it will be h del u by del x plus k del u by del t plus h square by 2 del 2 by del x square plus k square by 2 del 2 by del t square. And similarly, we have 2 hk del 2 by del x del t, and so on. And then on for the rest of the terms, fourth term is says with respect to x only, so it will be u xi tj minus h del u by del x plus h square del 2 u by del x square, and so on. For the fifth term, we will have twice 1 minus lambda, so there is no need to expand that. It will be uxi and tj. And for the last term, we will have xi plus 1. So we'll expand using the Taylor series expansion with respect to x direction. So it will be and so on. So after simplification or cancelling out the terms that are repeating, we will get 2k del u by del t minus 2 lambda h square del 2 u by del x square plus k square del 2 u by del t plus k cube del 3u by del t cube and lambda h square k square del 3u by del x square del t, and so on. So here lambda is nothing but k by h square. So from first two terms, we can take 2k common. So it will be nothing but del u by del t minus del 2u by del x square. And the rest of the terms are del 2u by del t square plus k cube del 3u by del t cube minus lambda h square k square del 3u del x square del t, and so on. So this term will become 0 as it is simply the heat equation. Then we will be left with Also, we will have some other terms like after expanding this, such as lambda, or we will be having in common that k square del for u by del x4. So when we take this term and this term, so we will be having k square del to u by del t square minus del for u by del x4 plus k cube del 3 cube by del t3 minus lambda h square k square del 3u by del x square del t. So this term will also is zero. It will also become zero as we have the heat equation, that is del u by del t equals to del 2u by del x square. So if we differentiate it again, then it will be del 2u by del t square is nothing but del by del t. So as it is a continuous, it can be written as del u by del t. We can take del 2x square by del by del x square outside. So it is nothing but again del u by del t is del u del 2u by del x square. So it will be del 4u by del x4. So we can say this term is nothing but 0. Therefore, we will be left with k cube del 3u by del t cube lambda k h square del 3u del x square del t. So from here, if you see tau ij is of order k cube plus k h square. So if we take for the order of the method, we have tau ij. So it is nothing but k square plus h square. So this is the order of the method for Crank-Nicolson. So this is the Crank-Nicolson scheme order. Here we can see that both in time direction and space direction, we will have second order. So it will be much faster and much accurate than the previous schemes, that is the Larsnes scheme and the Schmidt scheme. So up to here we have seen the truncation errors, the order of the schemes or different, that means the consistency. So we can introduce a term consistency. So any scheme in truncation error, we will do what, like say we have the different scheme, the Crank-Nicolson scheme. We will take all the left hand side terms to the right hand side and expand all the that ui plus 1j and all the terms using the Taylor series expansion and subtracting all the terms that are repetitive or all the terms that we can make zero. After that, whatever the first two or three terms that we are left with, we will consider our order for the method from those terms. So it is the procedure is same for all the algorithms. If you know the algorithm, the procedure for the skimmed scheme, like it is a simpler one. So the same criteria you have to apply here. Only the need is you required to know what is the Taylor series expansion. So using Taylor series expansion, you can find the truncation error for any scheme other than all these all. So yes, for order of the method, we will divide the truncation error by 1 by k, or you can say we will take k common. So what is consistency? A numerical scheme is said to be consistent if the truncation error tau tends to 0 as the step sizes hk tends to 0. So from the truncation error, you can see if you take h and k limit towards 0 and your truncation error is also going towards 0, then you can say the any numerical scheme that you have derived is consistent. The other term is stable, the or stability of a scheme. So a scheme is said to be stable if, or in a general language, we can say a scheme is said to be stable if error at one step does not amplify the error at the next step. Then we will say the given scheme is stable. Consistency can also be termed as compatibility. So the most important term is that convergence. If a scheme is not convergent, then there is no need for any such scheme in order to solve the numerical solution. It will give any spurious answers. So convergence is nothing but consistency plus stability. If a scheme which is both consistent and stable, then only we can say the given scheme is given scheme is convergent, and it will converge to the correct answer or the exact solution. So whenever we derive any scheme, we will first need to check its consistency, stability. Along both of these, we will say the given scheme is convergent. There is one theorem also. I don't know you have discussed it or not. So it is an important thing, that is Lax equivalence theorem. So it just states the statement that I have just said, that a consistent scheme is said to be convergent if and only if it is stable. So now we will discuss the stability of the above schemes. So for stability, yes, 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 in the x direction, space direction. Like, as we are here, we are like iterating in the time step direction, like at the what will be at the next time step. So, like order of the in truncation error, we are not dividing by 1 by k, but by finding the order of the scheme, we are dividing it 1 by k. So by order of the scheme, we mean how the faster or how accurate the scheme is with respect to the time, like how much time will it take or how much steps it require. So if it is second order, then it will be faster and like it will require minimum or lesser number steps than that of the linear scheme, linear or linear order scheme. Yes. So for stability, we will use a von Neumann stability analysis where we do is we will consider the solution of form UPQ. Like it is same as UIJ. We for the clarity purpose we have taken UP comma Q. That is nothing but xi to the power Q e to the power iota beta pH. So in order to determine the stability, we will consider the solution of this form. Here xi is an amplification factor, or this formula is obtained from Fourier analysis or Fourier series method. To find the stability of any finite difference scheme, we can use this method. So since xi here is the amplification factor, in order to any different schemes to be stable, this modulus of psi should always be less than equals to 1. If it is greater than 1, then again we do not this from the definition of stability, we have the error at the current level or current one time step does not amplify the error at the next time step. So if the amplification factor is greater than 1, then the scheme is said to be unstable. So first we will discuss the stability of the skimmed scheme. So the skimmed scheme is uij plus 1 lambda ui plus 1j minus plus 1 minus 2 lambda uij plus lambda ui minus 1j. So here we substitute the solution u pq xi to the power q iota beta ph. H is the again the step size or in the x direction. So we will substitute this solution in the our given skimmed scheme. So it will become that u from first term, that is uij plus 1, we will have xi q plus 1 e to the power iota beta ph equals to lambda xi to the power q iota beta p plus 1h plus 1 minus 2 lambda xi to the power q iota beta ph plus lambda times xi to the power q and e to the power iota beta p minus 1h. So from here you can see we can take xi to the power q common from both the sides. Then it will become, we will be left with xi We can take xi to the power q and e to the power iota beta ph common from both the sides. So we will be left with xi lambda times e to the power beta h plus 1 minus 2 lambda plus lambda times minus iota beta h. So this can be further simplified. We will take lambda common and we will be left with e to the power iota bh plus e to the power minus iota bh and 1 minus 2 lambda. So as you must know that e to the power iota x or that here we are using the von Neumann stability analysis method. So this formula is obtained from Fourier series method. So here xi denotes the amplification factor. So we will basically checking xi for every finite difference scheme, whether it is greater than 1 or lesser than 1. On the basis of that, we can say whether it is stable or unstable. So we have started with the schemated scheme. Uh, is it fine? We will proceed. So you, yes, we can apply it for all. Or you can just simply say this, it is said von Neumann stability analysis. Rafael, should I proceed? Okay. So you must be knowing that what is the that cos hyperbolic of x can also be written as, so using such kind of formula we can just simplify it, our given equation further. So it will be, so e to the power iota beta h plus e to the power minus iota beta h can be written as twice of cos hyperbolic, twice of cos beta h. Here it is not for cos hyperbolic, it is just simple for cos x. For cos hyperbolic, we don't have iota, and it will be plus. So it is cos x. So this one we have cos beta h plus we have 1 minus 2 lambda. So from here we will have minus 1 plus cos beta h times 2 lambda plus 1, or cos beta h minus 1 can be written as using the cos 2x formula. It can be written as minus 2 sine square beta h by 2 times 2 lambda plus 1. So from here we will have xi as 1 minus 4 lambda sine square beta h by 2. So for stability, we know that we must have modulus of xi less than equals to 1. So we will try to satisfy this condition. So we will take modulus of xi less than equals to 1. So modulus of xi less than equals to 1 will imply 1 minus 4 times sine square beta by h less than 1. So it is nothing but it is minus, from modulus we can have that it is the our this term xi is between minus 1 to plus 1. So it is 4 lambda sine square beta h by 2 less than 1. So subtracting 2 from both the sides, we will be left with, so from this, consider this one, we will have 1 by 2 greater than lambda sine square beta h by 2, or lambda is less than equals to 1 by 2 sine square beta h by 2. So since you must also know that sine square theta is between 1 to 0, so this in the denominator, sine square is always between 0 to 1. So we can say that it is 1 by 2. So this is our stability condition for a skimmed scheme. That is, lambda must be less than equals to half in order to be the skimmed scheme to be stable. So here lambda is nothing but k by h square, where k is a step size direction with respect to t and h is with respect to x direction. Yes. This step. Yes. Like here we directly substitute this solution, that is UPQ, this given form, in the our finite difference scheme, that is the skimmed difference scheme that is represented by star. Yes. Yes. Yes, here we just simply substituting, like in place of I and J, we have taken Q, P and Q. No, no, that is not a differentiation. Like here we also have iota, that's why we are not considering I and J. So in order to avoid the confusion, we are taking P and Q. Okay. So this is the required stability condition for the skimmed scheme. So you have also heard the terms during this week that unconditionally stable and conditionally stable. So from this we can say the skimmed scheme is conditionally stable. Only if the lambda is less than equals to half, then only the scheme will be stable. Next question, we will take the stability of the Lasnan scheme or the implicit scheme. So in Lasnan scheme, so first we will write the scheme. So the scheme was minus lambda times ui minus 1 j plus 1 plus 1 plus 2 lambda u ij plus 1 minus lambda ui plus 1 j plus 1 equals to uij. So this was our scheme. Uh, so here again we will substitute the solution of form using von Neumann stability analysis. It equals to, so we are just substitute this in our given scheme. We will have minus lambda times xi to the power q plus 1 iota beta p minus 1h plus 1 plus 2 lambda xi to the power q plus 1 e to the power iota beta ph minus lambda times xi q plus 1 e to the power iota beta p plus 1 h equals to, the last term is nothing but xi q plus e to the power iota beta ph. So we will just simplify, take the terms here, can we can also take the terms common xi to the power q and e to the power iota beta ph, and cancelling out those we will be left with xi times minus lambda e to the power minus beta ph plus 1 plus 2 lambda. We have taken xi common, so this will be minus lambda e to the power iota beta h equals to 1. So from here, again, we will use the trigonometric identities. So this will be minus lambda common, and it will be nothing but 2 cos beta h plus 1 plus 2 lambda equals to 1. So this is twice of lambda times 1 minus cos beta h plus 1 equals to 1. Now you can write it as 1 divided by 1 minus cos beta h plus 1. So we'll simplify it further up to the sine function. So after we substitute here 1 minus cos beta h as a already termed as sine function, it will become 4 lambda times sine hyperbolic beta h by 2 plus 1. So here again, you can see that sine square theta is always between 0 to 1. So let us denote it as d, the denominator. So always the denominator will be greater than 1. No matter what value of step size h you will take or lambda we will take, it will always be going to be greater than 1, which will implies that xi is always going to be less than equals to 1. So the Lasnan scheme is unconditionally stable. That means this scheme has no condition for stability. It will be stable for any value of the step sizes h and k. Now we will take another question, that the stability of Crank-Nicolson scheme, whether it is stable or not, and if it is stable, then for what parameters. So Crank-Nicolson scheme is given by 2 plus 2 lambda ui j plus 1 minus lambda ui plus 1 j plus 1 equals to lambda ui minus 1 j plus 2 minus 2 lambda uij plus lambda times ui plus 1 j. So again, we will substitute a solution of form u pq z to the power q iota beta ph. So we will see after substituting it whether it is stable or not. So after substituting, we will get minus lambda times z to the power q plus 1 e to the power beta iota ph 2 plus 2 lambda z to the power q plus 1 e to the power iota beta ph minus lambda z to the power q plus 1 iota beta p plus 1h. And similarly for the right hand side, we will have z to the power q e to the power iota beta p minus 1h plus 2 minus 2 lambda z to the power q e to the power iota beta ph plus lambda times z to the power q e to the power beta iota p plus 1h. So in this case, again, we will like take the terms common, that xi to the power q and e to the power iota beta ph, and simplify further. Then we will get xi times minus lambda minus beta h plus 2 plus 2 lambda minus lambda iota beta h, and on the right hand side we will get lambda times a to the power minus iota beta h plus 2 minus 2 lambda plus lambda times e to the power iota beta h. So here we will use again the trigonometric identities, that it will be minus lambda common will be 1 minus cos beta h 2 plus 2 lambda, and on the right hand side it will be lambda plus lambda times 1 minus cos beta h plus 2 minus 2 lambda. So this is nothing but it will be xi times 2 lambda sorry, it will be lambda times 2 cos beta h 2 minus 2 lambda. Now if we simplify this further, we will get 1 minus cos beta h plus 2 equals to lambda times 1 minus beta h plus 2. Simplifying further, we will get 2 lambda. It can be written as 2 sine square beta h by 2 plus 2 equals to, it can also be written as 2 sine square beta h by 2 plus 2. So from here we will get that xi is, taking 2 common on both the sides will be cancelled out. So we will be left with 2 1 minus 2 lambda sine square beta h by 2 and 2 1 plus 2 lambda sine square beta h by 2. So since we have that lambda is greater than 0, as lambda is nothing but k by h square and step size k and h are always greater than 0. So one can simply note that the denominator part, that is 1 plus 2 lambda sine square beta h by 2, is always greater than 0. Or you can say it will always be like that sine square is always between 0 to 1. So the denominator, that is in denominator we have 2 1 plus 2 lambda sine square beta h by 2. So if we take sine square is always between 0 to 1, so this term will be less than 1 plus 2 lambda. So the denominator is greater than that of the numerator. So again, as that of the Lassner scheme, we can comment that here xi, the amplification factor, is always less than equals to 1. Therefore, the Crank-Nicolson scheme is also unconditionally stable. So in similar way, you can find the stability of any kind of schemes or finite difference schemes. We will see a few more questions. Yes, 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 yes. Yeah, then it will be implicit. Like if we are finding it j plus 1 time step, we are only using the previous time step. Like j, if we are finding, suppose we had j equals to 5, and we are only using up to j equals to 4, like 0, 1, 2, 3, 4. Then it is explicit. But if we are using the solution at that level also, then it will be said to be implicit. Yes, yes. Like there are various kind of scheme. From these three schemes, you can like you can say that it is unconditionally for implicit. But we cannot be sure. Like there are other schemes also that are not discussed in the course. like some Richardson scheme or do Ford Frankel scheme, and other schemes are also there. So I cannot surely say whether it is always for implicit scheme only. It might be for the explicit scheme also. Yes, yeah, we have to check. Oh, so we will take a question that is like which of the following is true if an explicit scheme you can try this question. In this question, we have a heat equation, and you have to check if we try to solve this using an explicit scheme, then which of the following condition is true for stability. You can use that the previous we have discussed the stability of the scheme, like scheme scheme is obviously the explicit scheme we have discussed. So you have to check for which of the following condition the scheme is stable. Yes, lambda should be less than half. So we will see the solution for this. So basically, lambda is nothing but C kc square by h square. Since earlier we are considering the heat equation where the coefficient is 1, so that's why we are neglecting the C term. Here the C is 2. So as we have seen that the stability condition is that less than equals to half. So it says K is nothing but delta T and H is nothing but delta X. So we have delta T, delta X is given as 0.1 and C is 2. So this is H and this is K. So we just simply put in this form in this condition. So it will be twice of delta T divided by delta X square less than equals to half. So this one implies delta T should be less than equals to 1 by 4 times delta X square, which is nothing but 1 by 4 times 0.01, and it comes out to be 2.5 into 10 to the power minus 3. So this is a required condition for the stability of this above differential equation. The delta T should always be less than 2.5 multiplied by 10 to the power minus 3. So option A is correct. Next question we will see. Suppose we have a heat equation del U by del T equals to 2 del 2U by del X square. and it is solved explicitly. That is, we are using explicit scheme, and boundary condition is given as del u by del x equals to u at x equals to 0.5, with the initial condition is ux of 0 is 1 and x is from 0.5 to 0. So in this question, we have to find the representation of u5 comma j plus 1. That how does this term will look like? So here, in this question, what we are doing is we have a simple heat equation, and it is clearly shown that it is stated that we have to solve it explicitly, that we are using schematic scheme. But the boundary condition here is a derivative boundary condition, or you can say Newman boundary condition. So we need to find the term u5 j plus 1 of the schematic scheme. So firstly, we will see what is a schematic scheme. Yes, we will discuss the implicit scheme also. So in this one, you can simply write your schematic scheme or the explicit scheme as so first we will need the schematic scheme, and the schematic 1 minus 2 lambda plus uij plus lambda ui minus 1j. So we need to find what is the value at u5 j plus 1. So here, if we put I equals to 5, then we will have u5 comma j plus 1 lambda u6 comma j plus 1 minus 2 lambda u5 comma j plus u4 comma j. So here we are also using in this, like you can see, u6, but x is only from 0 to, we have given that x is only from 0 to 0.5. So we are only with these number of points, 5 points, but we also need the value at point C. For this type of case, we will use the derivative boundary condition. So derivative boundary condition states that del u by del x equals to u. So we just simply substitute the central difference scheme for the first order derivative, and it says ui plus 1j minus ui minus 1j divided by twice of delta x equals to uij. So here you will get ui plus 1j equals to twice of delta x uij plus ui minus 1j. Now here if you take I equals to 5, then you get u6 comma j equals to twice of delta x ui comma j u5 comma j plus u4 comma j. So we are at this step earlier. So here we do not have the value of u6 comma j, but from this using this derivative boundary condition, we will get the value for the u6 comma j. So after substituting this in our given equation, you will be left with u5 plus 1 is nothing but u5 comma j plus 4 times of lambda u4 comma j, or you can, if you substitute this equation 2 in equation 1, you will have lambda times twice of delta x u5j plus u4j and 1 minus 2 lambda u5 comma j plus lambda times u4 comma j. So it will be like delta x we have zero point 0.1, so it will be, or sorry, delta x we have 0.5. Oh, or we don't need to substitute delta x value, so it will be u5 comma j plus 2 lambda delta x u5 comma j, and we have one more 1 minus 2 lambda times u5 comma j plus lambda u4 comma j, again lambda u4 comma j. So from this equation we have u5 comma j plus twice of lambda can be take common, so it will be minus 1 plus delta x u5 comma j plus twice of lambda u4 comma j. So you can simplify it as this. So this is the required iteration at that point, that is u of 5 comma j plus 1. So the boundary conditions will be like beneficial, as we have discussed in our first session. We have three types of boundary condition. That is the Dirichlet boundary condition, Newman boundary condition, and the mixed boundary condition. So Dirichlet boundary conditions were the standard one that are we have seen at some point, let's say A given at UA and some ending point B is UB. So these are the Dirichlet boundary conditions. And if we have del U by del X equals to some U or say UA, such kind of conditions are called Newman boundary conditions. So these conditions are come into use in case we need a value at a point which is not included in the grid along which we are finding the solutions. So using these boundary condition, we can simply, using the central difference forward or backward any of the scheme, whichever is applicable, we can find that value of those at that point and simplify answer to in order to obtain the answer. So these are the importance of the boundary conditions. So I will stop here and I will discuss other examples, one or two more examples on the implicit scheme next time. So if you have any doubt, then you can ask. Yes. In these topics, I have basically discussed what are the schemes discussed and included the assignment problems, like what how to find the stability and consistency or other things that I have included along with the schemes also, scheme itself. Like instead of solving the assignment problem separately, I have included it there. Like whatever previous, I have to solve the previous assignments. So previous assignments include the stability or consistency of the finite difference schemes. Like or we can include like much more numerical solutions that as the last example or the last two, three examples. I will try to include much more. Yes, yes. Like those questions you have to try with the same concepts that have been taught in class or I am using in this lectures. Like the questions won't be same. The like here we are just simply solving the partial differential equation or the basic difference schemes like Crank-Nicolson scheme. Or you can be like given a other differential equation part that del u by del t plus del u by del x, not a heat equation. There you have to apply the similar concepts only. Or as per the assignment problems, like in assignment problems, there also the stability and truncation errors are included, but there they might change the partial differential equation. As I have said that you have to follow the same fashion, like while solving for truncation error or while solving for the stability, the concepts are same for all. As per the numerical, these questions you can do it by yours. Like I have discussed few numerical problems. So here we have to do nothing but just have to put for each iteration like j equals to 0, 1, 2. That you can cross check by yourself also. Okay. Uh, do you have any other doubt or I can end the meeting? Like okay. So if you have some like say some grid, like this is x and this is y. And suppose we taking y minus 2 to 2 and x minus 2 to 2. So if we discretize this with a step size of 1 and y also 1, so this kind of grid we will get. So this, sorry, which you are discretized boundary points, right? So the points on the boundary, I will highlight these. So these are the boundary points, those are included in this grid. So these number of points will be said to be the discretized boundary points. So as you can see here, the number of points are 16 points are there. You can count that these are 5 points on this line and 5 points on the bottom line. And on both the sides, we have three more points. So the total number of discretized boundary points will be 16. And when we have to talk like the nodal points, so the nodal points are the total number of points included in this grid. So it will be like 16 on the boundary, and inside there are 17, 18, 19, 20, 21, 22, 23, 24, 25. So total points now, nodal points will be 25. The all points that are there on the grid or whichever domain we are solving. Is it fine? Yes, both. The total number of points. Yes, we can have like a big domain or the step size is smaller. I'm not sure, like either it will be 2 to the power 4 for boundary points, it can be. I will check and tell you. Like discretized points, boundary points are the points on the boundary, but there's a specific formula using which we can solve for the larger grids. I will check this one. Oh, yes. Like in this class, I have discussed only with respect to X. So in the like lecture notes, you have to, you can see that it might be up to y by del. So you are just have to extend the same concept. For X, we are using central difference scheme. For X, okay, okay. For that, you have like a standard equation, the second order equation. So you don't have to take the partial derivative with both x and y. You have to only consider the del 2 by del x square, del 2 by del y square, and del 2 by del z square. So there will be a matrix, and on like examining the eigenvalues of the matrix, you can comment on whether it is the class. You can either classify the partial differential equations. Like you have to just extend the concept you have read for x to up to y. If you have up to y, then you can similarly up to x, z, and all the parameters. Yes, here u is x of t, x function of x and t. Yes, 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 yes. It would be same, I think. Yes. 1 second, sorry. Uh, yes, you can comment on that. Like either it will be 1 second, please. So here, as you have seen that you have given like two values, initial condition, we have two, like we have divided. That so if it either it will be mentioned in the question that if either it is symmetric or not, or either you can find it by yourself that if you take 1 point that side and one less than half and one greater than half. So mostly while we solve the numerical solutions in this course, the it will be always be symmetric. Yes. Okay. Thank you so much. I will end the meet. Thank you for joining. Yes, yes, you will get. The for the last class, I think I have uploaded the link. I don't know how it will be shared with you. Actually, in the last class, like I have started the class, but after 5 or 10 minutes, the video stopped. Recording has stopped. So I noticed it after the 2 hour class. So actually, I have no, it is there, but I have recorded it again. So initial 5 minutes were there that were recorded with you. The rest of the video I recorded again alone. So yeah, actually, I haven't noticed that it has stopped, but after ending the class, I have noticed it was only for the first 5 minutes. So I will upload this one also. I think his mail ID is available in discussion forum. No, his also is there, I think. I have checked. Either you can share it here or okay. So either he will share it again. So thank you for joining. Okay, thank you. Yes, I'm a research scholar. I'm doing my PhD here. I'm from Delhi. Native place is Haryana, but I live in Delhi. Okay, so you are where from? Okay. Like these are like much more calculative. The course is easy, but if you like the concepts are same throughout the course. Like for every scheme, you have to repeat the same things. But while calculation, you might miss something or miswrite something, then it will create problem. Otherwise, there won't be much. Only the calculations are there. Okay, thank you so much.